SwayamPrabha. Digital India. Educated India.
Yes, good morning friends. In the last lecture we were discussing about the thrust required, power required for a cruise flight, right? And we also found out a condition: if I want to fly the machine with thrust required minimum, then what should be the CL with which I should fly? And we also found out an expression: if I want to fly the airplane in cruise mode in power required minimum mode, then what should be the CL with which I should fly, right? If I write those things, V for thrust required minimum, the expression we got was something like this: 2W by S and rho CD naught by K, and V for power required minimum was 2W by S rho under root 3 CD naught by K. And please remember, these are all pertaining to cruise flight. This we should not miss. Cruise. And more pictorially, we know that these are the basically schematic of different flight paths an airplane will be taking, and we are concentrating here, which is the cruise phase. So the message here is very clear for a designer. If I want to fly the machine for a cruise and I want to ensure that thrust required is minimum, that means drag is minimum, then I need to fly at a CL, thrust required minimum, this is basically drag minimum. I need to fly at a CL such that CL equal to CD naught by K, which actually means KCL square is equal to CD naught. This is KCL square. This is the induced drag component. Why this induced drag is there? That's because of lift. So we call it lift induced drag. And at a speed when this induced drag component and the parasite drag component in terms of coefficients, if they are same, and only that at that point if I am flying the machine, which actually means I am flying at a CL equal to CD naught by K, which also means I am flying at a velocity 2W by S by rho CD naught by K under root, I will be getting thrust required minimum, right? If I have a closer look here, I could see that if W by S, if the wing loading is less, then velocity or speed required for thrust required minimum also will be less, right? Similarly, for speed for power required minimum, if wing loading is less, the speed for power required minimum also will be less. And when I say speed will be less, it has a direct impact on the engine. That means I will be requiring a lesser rated engine, the engine weight will be less, and engine complexities will be less, right? So designer will, depending upon the different conflicting requirement he has, he will actually select W by S, and at the end of this course you will realize how do I select a wing loading for a particular airplane which will satisfy best of all those flight phases. Sometimes or many a times the designer has to give a weightage. What is the primary role of this machine? If it is for a cruise, for a transport airplane, he may give more weightage here. If it is a fighter airplane, he may give more weightage towards the maneuver or takeoff distance or landing distance. So all these things will come, but before we educate ourselves to take a decision on this, we are trying to build the basic understanding, right? Now let us see. We have also seen this thrust required versus speed or velocity. The graph typically goes like this, and this is the point where the V for thrust required minimum. Please remember, thrust required is equal to the drag. So when I say thrust required minimum, I am implicitly telling that the drag required minimum, right? Now come back to the engine. The airplane has an engine, right? It will be delivering some thrust. Let's say I am drawing typical representation of thrust from a jet engine, turbojet type. I can fairly assume it is constant and it remain almost constant, though in practice you will find there are secondary influences on the speed as well. Now see, there are two interesting points. Suppose allow me to extend it like this. So I have got one point here, I have got one second point here. Let's try to understand what are these points. What is this point? At this point, you could see that the drag required, which is given by this graph, because this is thrust required, and we know thrust required equal to drag. So at this point, whatever engine is supplying, that is, we call it thrust available. At this point, they are same. That means if I am flying at this speed, this is the maximum speed, and I will be going without any acceleration, right? Constant speed. But if I want to fly at some point here, you could see here. Here I see that if I am flying at this speed, there is an excess thrust. This excess thrust can accelerate the airplane, it can lift off the airplane, so many things it could do. So this is one concept of excess thrust. Similarly, we will see excess power. These two are very important concepts, and we will see how this concept can be utilized to analyze an airplane performance in terms of rate of climb, in terms of acceleration, without changing the altitude. All those things we'll be discussing. But before we go to that, let us ask a question. Let us say the airplane was flying at this point 2, and because of certain reason, the velocity has increased. Is this clear? Suppose it was flying at speed, let's say I call it Vm, and because of certain reason, the velocity has suddenly increased. What this graph tells you? The moment the velocity increases, you could see now the drag is more than the thrust available from the engine. So it will automatically decelerate. So it will have a tendency to come back to this point. And suppose for some reason it is now flying at a lower speed, then what happens here? The thrust is more than the drag, so it will accelerate the airplane towards this point 2. So we say, as far as velocity stability is concerned, it is statically stable at point 2. I repeat again, suppose I am flying at point 2. If for some reason the velocity has increased, from this graph we could see now at this point the drag experienced by the airplane will be more than the thrust given by the engine, so it will start decelerating, so it will have a tendency to come back to this point. Similarly, if it is flying at a speed less than Vm, the thrust will be more than the drag experienced by the airplane, so it will have a tendency to go back to this point 2. So we say at point 2, the aircraft is statically stable in terms of speed is concerned, right? But if I try to see here at point 1, suppose I am flying at point 1, here also thrust and drag are equal. If for some reason there is an increment in the speed, what will happen? See, any point beyond this, the moment there is an increment, the thrust is always more than the drag, so the airplane will go on accelerating, and this point will never come back to this point 1. So at this point, it is not statically stable in relation to the speed. Okay. Also, there should be another point should come to our mind. For any airplane, there is something called a speed called Vstall, which we have discussed, right? Vstall is the speed, the lowest speed with which it can manage lift equal to weight. That means he is actually putting CL to CL max. He has put all the flaps down and angle of attack, the maximum. If you recall, this is CL versus alpha is something like this. You are flying somewhere here, so this value is CL max, and Vstall will be equal to 2W by S rho CL max. So this decides your minimum speed limit, that if the airplane goes below this speed, it is of no worthy as far as flying is concerned. That means for all practical purpose, for us, the relevant speed or velocity will be which are greater than Vstall, okay, or greater than equal to Vstall. Now, if you again revisit power required versus speed or velocity, the graph is also, this looks like this, and let's say this is the power available. It's typically a propeller IC engine combination where the power available almost remain constant for practical purpose as far as understanding the basic physics behind it. In actual practice, please remember, there are secondary effects. We'll be talking later. Now let's see here. Here this gap. We know that, by now we know that this is the V for minimum power, right? But what are these lines? This gap is, as I was mentioning, this is excess power. And let us see how can we utilize this excess power in adding value to the performance of an airplane, right? When I say power available, please also understand, when I say power available or thrust available, they all will go on changing with altitude, right? So whenever I draw a diagram, it is for a fixed altitude. For all our convenience, in our discussion, you can take this as a sea level condition, and as the lecture progresses, we will give a correction to it as we gain the altitude, right? The physics doesn't change. Let us draw this diagram. This is a typical schematic representation of an airplane which is not cruising, it is now climbing. Okay? We say it is climbing, or flight phase is climbed. Let us see here. If I now try to write the force balance along the velocity direction, along this direction, what do I get? I get, of course, there is a thrust. So I guess T minus D minus W sine gamma is equal to M dV by dt. What are the assumptions here when I have written this equation? First of all, I'm assuming that thrust and velocity in the same direction. Number two, I'm assuming that the mass is remaining constant, and of course alpha is very small. So if this is the equation, and if I am discussing only static performance, which actually means that steady state performance, so we are not taking any acceleration, right? Then I can simplify this equation from T minus D minus W sine gamma is equal to 0. With no acceleration, it's a static performance. So what happens now? T minus D by W is sine gamma. What is gamma? Gamma is the, we know very well, gamma is the flight path angle. Flight path angle. That is the velocity vector mixed with the horizontal. So how it is climbing? The velocity vector with the horizontal is in the flight path angle or climb angle. So what is the message from here? If I am to fly the airplane at a particular climb angle, I should ensure that it has enough thrust to compensate drag, and this relation should be valid, right? If I now multiply both side by V, what happens? So this will be T into V minus D into V by W is equal to V sine gamma. Right? I multiply both sides by V. What is this TV minus dV by W? Let us understand this. T into V is what? This is basically thrust into velocity or speed. So this is the power available. That is power available from the engine at a given altitude. What is D into V? It is the power required. So what is TV minus dV? So TV minus dV is the excess power. Remember, we are talking about excess power. So now and what is V sine gamma? See here, if this is V, I can dissolve this into two components. V sine gamma is the vertical component. It is the speed at which the airplane is going up, and that is called rate of climb. Rate of climb. So now if I use this equation, I can write rate of climb equal to excess power divided by W. Okay? Now if you again go back and recapitulate what was the diagram, this was power required, so speed, and let's say this was the power available. Then this gap, they are the excess power. This is what is this. And this excess power is linked to rate of climb. So now, understanding this, understand this diagram, can you answer a question, at what speed should I fly to get maximum rate of climb? You could see here, the excess power goes on increasing and comes to a maximum value here, and then again goes on decreasing. And we know rate of climb is linked to excess power. So I know that V, where the excess power is maximum, is that speed I should fly to get rate of climb maximum. So could you understand the linking of excess power to rate of climb? This concept will be utilized in defining few more parameters which are very, very important for aircraft performance. Yes, welcome back to this additional session. Let us revise what we have covered so far. We were focusing on cruise flight. And what do you understand by a cruise flight? Cruise is, it is a unaccelerated flight. Number one, unaccelerated flight. And when you say level cruise, level means wings level. Okay, the typically it is like this. If I am doing a cruise, I am going to constant speed, wings level, not like this, wings level like this. And also, I am ensuring that there is no change in the altitude. So I say third point, the altitude fixed or they remain constant. Right. This we have understood, and once we understood what is a cruise flight, we try to understand what is the thrust required to maintain a cruise flight. And in that, we realize that thrust required can be modeled as CL by CD, W divided by CL by CD. And we also understood that to have thrust required minimum, CL by CD should be maximum. And for that, we realize that to have CL by CD maximum, to have thrust required minimum, we need to fly at particular CL, which is given by CD naught by K. Then we try to understand how can I plot the variation of thrust required versus speed, and we realize that thrust required will follow this trend, and we also understood at higher speed, since CL required for maintaining lift equal to weight is less, it will have lesser induced thrust required or drag, which are same. And typically there is a point which is, if I fly at a velocity as given V star, for which CL by CD is maximum, then I have thrust required minimum. Right? I also understood how to calculate thrust, because we know thrust is W by CL by CD, and from drag polar I know CD equal to CD naught plus KCL square, and for level flight CL is nothing but 2W by rho V square S. So given weight, given speed, given density, that is at what altitude I am flying, given the wing area, I know CL. K I know because K is 1 by pi aspect ratio E. So I can calculate CD, as I also know the CD naught is fixed for an airplane for at low speed. So once I know CD, once I know CL, I know CL by CD, I can find thrust required at different speed, and I have plotted that thrust required different speed in this figure, right? And in that we found out that there is a particular speed at which thrust required is minimum, and that corresponds to a case where CL by CD is maximum, and for that CL is CD naught by K. Right? Once we are through with thrust required, we try to also understand if this is the engine which is supplying thrust from the engine, say for typically a jet engine, then the point of intersection here will give me the maximum velocity. Okay, that is the time when I have put the throttle of the engine full, and at that point the thrust available and drag thrust required are same. So this is my Vmax. This also we have understood. After that we went for power required. We went for power required, It was straightforward for us because this is the power required at a cruise. That means power required with a constant velocity. For that, power required is thrust required into V, and we already know thrust required is W by CL by CD into V, and V I also know because it's a cruise, so lift equal to weight, so V is nothing but 2 W by S by rho CL. So once I know V, once I know CL by CD, I can find the power required. And in this, when we substituted V here, we realize power required will be proportional to CL3 by 2 by CD. And for power required minimum, we realize that CL3 by 2 by CD should be maximum. Unlike for thrust required minimum, it was CL by CD maximum. And like for thrust required minimum, this translated into CL equal to CD naught by K under root. For power required minimum, we found this translated into CL equal to under root 3 CD naught by K. We also realize that if I want to fly at CL equal to CD naught by K, that is thrust required minimum, then the CL required to fly at thrust required minimum is lesser compared to CL required to fly at power required minimum. Therefore, the velocity required to fly at thrust required minimum will be higher compared to velocity required to fly at power required minimum. So, V power required minimum is less than V thrust required minimum. Once we understood this, we also tried to see what happens if an airplane goes on climb, and there we also realize that the TV minus dV by W as rate of climb. This TV minus dV is nothing but the excess power, right? What is TV? T is the thrust available into V, so power available. And what is dV? dV is the power required to overcome the drag, right? But there is a catch. When I am doing a climb, let us understand, when I am doing a climb, then lift is W cos of gamma, where gamma is the flight path angle. When it is a cruise, then lift equal to weight. So you could see that CL is 2W by rho V square S into cos gamma, and for CL in this case is 2W by rho V square S. So which one is greater? Since here there is a cos gamma, you could see clearly that CL during climb is less compared to CL during cruise, right? That means the induced drag for climb is less than induced drag cruise. That in totality means CD cruise is greater than CD climb. So when I interpret this you understand, because CD is nothing but CD naught plus K CL square. Okay. So that means if I come back here, I need to understand that d into v in this case is not the power required for cruise. It is the power required for climb. This distinction I must have. Although for gamma less than 15 degrees, for all practical purposes, they are same, right? Or comparable. So you don't make much of a mistake. But fundamentally, we need to understand that while in climb, d into v is the power required in climb, which is less compared to power required in cruise, keeping other thing same. We also realize that this power required versus v, if I draw it like this, and if this is typically for a IC driven propeller combination engine, then this is the Vmax. And for jet engine, if I want to draw it like this, again if this is the power required, then jet engine, this is the power available. This is for jet engine. You could see this point is the Vmax. Okay. But as a designer, we need to understand also that if I am coming for a landing, right, I'll be operating somewhere here, right? So I have got enough excess power. So in case of any eventuality, I can use that excess power to come out of it. However, when I am using a jet engine, you could see that this excess power near the stall or near where you're landing, that time the excess power relatively is less compared to for such engine. So this is one distinction a designer need to keep in mind. What happens if we go higher and higher? That is, more specifically, how the power required is going to vary with altitude, how the velocity required is going to vary with altitude. So this is important because, please understand, we are writing power required versus V, plotting it like this. This is fixed to an altitude. As I am going higher and higher, the density of air is reducing, so that will have an effect on this. Second thing, power available. Again, as I am going higher and higher, density is going to reduce, so this will also have an effect on this. This will try to come like this, and this will also try to shift. Let us see how we can guess, we can estimate how this variation will change with altitude. That is exactly we will be doing now. V we know for cruise is 2W by S by rho CL. So let's say at sea level, we denote it as V naught as 2W by S rho naught CL. So this V naught, this represents sea level condition. Rho naught is sea level density. Okay. Similarly, power required at sea level will be, we know this expression, 2W cube CD square by rho naught S CL cube. Right. Now let us assume that we are still flying at same CL, but we are going higher, so different altitude. So what does it mean physically? If I am keeping same CL, let's say I am at 1 kilometer, I am having lift equal to weight. Now I want to fly at 2 kilometer, so lift is still equal to weight. So for that, since density has reduced, I must compensate that loss of lift through velocity, increasing the speed, if I am keeping the CL same, right? because CL is achieved by the orientation of the airplane, right? Whatever CL is required, I have to orient the airplane in such a way, I have to get such an angle of attack so that CL is what CL desired, right? Now we are keeping the same CL, so we have to compensate through velocity, okay? So now what we can do for same CL, we can write V altitude is equal to 2W by S by rho CL. So I am not changing CL because we are trying to see that what is the effect if you keep the CL same. But you can notice that now rho is not rho naught, rho is rho at some altitude. Similarly, power required at altitude will become 2WQ CD square by rho SCL cube. Again note that it is rho, not rho naught. So using these two equations, I can write in a combined way V altitude equal to V naught, rho naught by rho to the power half, and power required at altitude is equal to PR naught into rho naught by rho to the power half. So what is the meaning of that? It's very clear. As I am going higher and higher, the rho value is going to become lesser and lesser. So this ratio will go on increasing. I need higher velocity to fly at same CL to maintain lift equal to weight. Similar story is also here. So the power required suppose this was sea level, as I write sea level condition. Now I can see from there, as I am going to fly at a higher altitude keeping same CL, the velocity which was here, now I require higher velocity, so you will find the graph. This is altitude, then further this is higher altitude. Okay, what happens to thrust or power available? The power available was, let's say here, typically for IC engine propeller combination. As I go higher and higher, this man goes down, this man rotates upward. So there is a, as more and more you go, this gap will go on reducing, right? So there will be an altitude where you will find, if this is the power required, the power available is just matching here, and this is the point where you have absolutely no excess power for rate of climb, right? And that is defined in our aerospace industry as absolute ceiling. That is, we call absolute ceiling. That is, it is that altitude at which the rate of climb, maximum rate of climb is 0. Right? Okay. So how it is generated? If I draw a graph, this is altitude, the variation can be, and this is maximum rate of climb. Okay, the graph is something like this. Here, this altitude is called absolute ceiling. Okay? And we, for practical purpose, we define an altitude which is called service ceiling. It's called service ceiling. Service ceiling is that altitude at which the maximum rate of climb is not 0, but it is 100 feet per minute. For all operational purpose, we use service ceiling, not absolute ceiling, right?